Okay, in this video, we're continuing with chapter 5, but we're shifting gears a little bit. We were talking about antiderivatives. In this section, we're going to be talking about area, and later on, you're going to see how these are related to each other. So if it seems like we're doing something unrelated, you're kind of right, but you'll see how they're related later on. So we're talking about area, and what we're going to do in this section is actually give a definition for it. So you know specific area formulas that you learned in elementary school or middle school for triangles and circles and stuff like that. But what we want to do is figure out a general approach for figuring out pretty much any area, assuming we have some relevant formula or equation. So just to make things concrete, I'm going to do various examples with a region I'm calling R. And I have a picture here. So it's bounded by x equals 0, which is the y-axis, x equals 12, the x-axis, and the curve y equals 225 minus x squared. And it might be convenient to call that f at some point, so I'll just file that away. So here is a picture. My y scale is much different from my x scale, but here's the gist of it. It's this four-sided figure where 1, 2, 3 of the sides are straight, but the top is curved. So we don't have a formula for this. It's not a rectangle, it's not a trapezoid, it's not a circle, it's some exotic thing. So let's just think about estimating the area. Sort of a trick that gets used in calculus a lot is figure out how to estimate something, then try to run a limit on your estimates, and that turns it into the correct answer. So how could we estimate the area of R? So there are a lot of ways we can do this, but basically here's what we want to do. We're going to use rectangles. Okay, that's not the only way to do it, but that's going to be the easiest way to do it. We'll decide how many rectangles we're going to use. We'll divide the base of the region. So we're going to think of this as having a base along the x-axis into a certain number of intervals, 1 per rectangle. For ease, we'll choose a consistent method of estimating the value of the function on each interval. We'll do base times height, and then we'll add our results together. So I'm going to do several examples of this so you can start to get a feeling for it. So here's example number 1. We're going to use 3 intervals in what's called a left endpoint approximation. So here's what I'm going to do. And this is one of these things where even if you're taking notes on this, you probably don't need to copy everything that I'm doing. It's better to watch and think, and then in the exercises, you'll do it yourself. So this base is 12 units long. If I divide it into 3 intervals, each one is 4 units wide. So I have one that goes from 0 to 4, one that goes from 8 to 12, and one from 4 to 8. So I'll color them differently so you can distinguish them. Now, I am going to approximate this region, R, using 3 rectangles. And here we're using what's called a left endpoint approximation. So my first interval is down here. Here's the left endpoint at 0. So just for convenience, I am going to draw a rectangle that is exactly as tall as the graph is at this left endpoint. And then I'll just make that go straight across, and I'll continue my rectangle like so. Do the same thing for the second interval. Here's the left endpoint of the second interval. How tall is the graph at that left interval? And I'll make that the height of a rectangle. Same thing over here. There's the left endpoint of the third interval. How tall is the graph at that left endpoint? Make that the height of my third rectangle. So we have 1, 2, 3 rectangles. And we just did a really simple, straightforward method of saying, let's just make this rectangle as tall as the graph is at the left endpoint. So what you might notice is that the total area of these rectangles is an overestimate of the actual area we're trying to find, because these rectangles go above the region some of the time. So what is our estimate? Well, let's just figure out what the areas of these rectangles are. So I'm going to make a little table. So I'll have rectangle, the rectangle number, its base, its height, and its area. So rectangle number 1, its base is 4 units wide. What's the height? The height was however tall the graph was at 0. So that would be f of 0, which is 225. I'll just remind you that the graph was 225 minus x squared. So the area of that first rectangle is base times height. 4 times 225 is 900. And remember, the scale here is very different. This rectangle is 4 units wide and 225 units tall, even though it doesn't look like that. All right, rectangle number 2 has a base of 4. The way we're doing these, we don't have to do this, but the way we're going to do it to be easy is to make all our rectangles the same width. The height of my second rectangle would be f of 4. F of 4 would be 225 minus 16, which is 209. So the area of my second rectangle would be 836. My third rectangle has a base of 4. Its height is f of 8. F of 8 would be 225 minus 64, which is 161. Multiply those together, and that's 644. If I add all this up, what do we get here? That's 80. So it looks like 2380. Hopefully I'm not goofing the arithmetic. Just so you know, this is the groundwork to go other places. So we're actually more interested in this technique than we are in the particular number most of the time. If this were an AP free response problem, you could just say your answer. You could, so this is sort of an aside, but on the AP, it would be totally fine if you wrote your answer like this. And in fact, that's kind of superior because this showing your answer this way makes it very clear what you did. If you just mysteriously write 2380, it's not clear. Just leaving this, right, it's super obvious, base times height plus base times height plus base times height, and you don't have to worry about the arithmetic. Okay, now, this was just one of the ways I could have done this. Let's look at another example. 4 intervals and a right endpoint approximation. So if I'm using 4 intervals, each one is 3 units wide. So one goes from 0 to 3, 3 to 6, 6 to 9, and 9 to 12. And again, I'll just alternate the colors so that they can be distinguished. And now here I'm using what's called a right endpoint approximation. So in order to determine the height of the rectangle, and again, we like to just determine the height of the rectangle in a really easy, consistent way. So here we're just deciding, let's always use a right endpoint. So here's the right endpoint of my first interval, go up here, that's the height of my first rectangle. So what you'll notice here is, in this case, the rectangles are all going to be below the graph we're trying to find, so it's an underestimate. For my second interval, here's the right endpoint. That's the height of the graph at my right endpoint. Turn that into a rectangle. Same thing over here. Here's my third rectangle. Here's my fourth. And what would our estimate be here? So rectangle, base, height, area. Each one has a base of 3. For my first rectangle now, its height is f of 3. Because my right endpoint of the first rectangle is at x equals 3, and we're just measuring how tall is the graph there to get the height for this first rectangle. So f of 3, again, let's just have this written someplace easily. F of x is 225 minus x squared. So that would be 216. If I multiply that out, that looks like it's 648. My next one ends at x equals 3. So what you'll notice here, if you start to get good at this, you don't even have to draw the rectangles, you can simply understand the pattern. If I'm using a right endpoint, then 3, 6, 9, and 12 are my right endpoints. So 225 minus 36 is 189. 225 minus 81 is 144. 225 minus 144 is 81. So what do I have here? This would be 2, oops, sorry, not 2. Sorry, I'm blanking on this. So 567. I should have had a calculator handy. Maybe I'll grab one in a second. This one, if we multiply it out, it's going to be 432. This one is 243. If I make an arithmetic mistake, don't really stress over this. Again, I'm more interested in the technique than I am in the final answer. But what is our estimate here? So 15 and 5 is 20, 6, 12, 15, 19, 7, 12, 16, 18. So you'll notice we have vastly different estimates because one of these is clearly an overestimate. We have all this extra area above the region inside our rectangles. And this one's an underestimate because there's all this stuff we're missing. The true answer is somewhere between these numbers. All right, let's try one more. So here, hopefully it's going to be a lot more accurate because I'm going to do two things. First, I'm going to increase the number of intervals. I'm going to do 6 of them. And I'm going to use what's called a midpoint approximation. So for each rectangle, I'll measure the height not of the left endpoint or the right endpoint, but in the middle. So here they're all 2 units wide. And I'm going to measure their height at the midpoint. So for my first interval, my midpoint is at x equals 1. So here would be my height at x equals 1. I'll draw on a dotted line, at least for this first one. We're going to say the height of the rectangle is the height of the curve at that midpoint. And we'll draw a horizontal segment through there. And I was doing this in purple. Here is my first rectangle. Here's my second midpoint. Here's the height of the curve at that midpoint. Here's my third midpoint. Here's the height of the curve at that midpoint. Here's my fourth midpoint. Here's the height of the curve at that midpoint. Here's my fifth one and my sixth one. So here, what we're going to have is a case where it's not clear if this is an overestimate or an underestimate, because our rectangle is sometimes above the curve and sometimes below the curve. And I don't want you to think that those errors will perfectly cancel out, but hopefully this will be much more accurate than what we did before. Because what we did before, we had cases where something was clearly an overestimate or clearly an underestimate. And in this case, it's not clear one way or the other. Right? This third rectangle, for example, it's an underestimate over here and an overestimate over here. Those areas are very similar. So it's like those two errors might cancel each other out and we'll get something quite accurate. Please don't feel like you have to do this along with me. I just want you to see one version of the picture. You will be practicing these in classwork and homework. Don't feel like you have to pause the video to copy this picture. So what have we got here? My first rectangle. So all of my rectangles will have, here, I'm not even going to label them. They all have a base that's 2 units wide. For the height, it would be f of 1, f of 3, f of 5, f of 7, f of 9, and f of 11. Those are my midpoints, and I'm measuring the height of the curve at each one. So this is 224, 216, 200. This would be 176. This is 144, and this would be 104. And I'm doing these in my head really quickly, so it's possible I've made some sort of error. So what are our area estimates? 448, 432, 400, 352, 288, 208. And if I add these up, let's see, 10, 28, 6, 9, 14, 22, 10, 17. So I did this really quickly and potentially there's an error, but now this is my estimate, right? We still don't know really what that area is, but we're estimating it in different ways. Our first estimate was 2380, and we're sure that was too big. Our second was 1890, and we're sure that was too small. Here we got 2128, and that one, we're not going to say that's absolutely the correct answer, but we have a lot of reason to believe that's accurate. So what I'm saying here is right now, we're not overly concerned with which estimate is best. But we want to understand that there are various ways of going about this. And what's actually most important is how many intervals we use. You might feel like, oh, midpoint is great. But I'll tell you, if we had done left endpoint with 100, that's probably better than doing midpoint with 6. Right? The idea is if I have enough rectangles, right? So if I have some curve like this, if I have literally hundreds or thousands of rectangles, then each rectangle is so narrow that it barely matters whether it's a left endpoint or a right endpoint. You could sort of imagine that we might just have thousands of really, really skinny rectangles in here. And once we finish with that, we really can't tell the difference between the total area of all the rectangles, all these super skinny rectangles, and the total area of the region itself. So just kind of file that away. Yes, under certain circumstances, we might prefer one way of doing this, left endpoint or right endpoint or midpoint or something like that. But what really is going to drive the accuracy is how many we're using. We want lots and lots of really skinny rectangles. So now we're going to abstract this a little bit. So I'm going to give you a definition. Suppose the continuous function f, so we're assuming the function we're dealing with is continuous, takes positive values on the interval AB. So we're simplifying things. We're assuming this function has positive values and is continuous. We're going to divide the interval into n congruent subintervals like we did before. And we're going to choose a point from each one. So this is actually a little typo here. The stars should all be superscript. So basically, what I'm saying here is from each interval, pick a point in some way. So we saw 3 examples where the first time we always picked the left endpoint, the second time we always picked the right endpoint, the third time we always picked the midpoint. But basically, I'm just saying these starred numbers are the points we picked to measure the height. Generally speaking, we'll do it in some consistent way that's very easy. Right endpoint all the time, left endpoint all the time, midpoint all the time. Those are the easiest ways. Delta x here is b minus a over n. So just for the example we did before, the interval from a to b was from 0 to 12. So b minus a is 12. We're going to take 12 and divide that by how many intervals there are. That gives us the width of each interval. So we can estimate the total area by basically doing, this is my base, this is my width of the rectangle. F of xk star is just a fancy way of saying in each interval I'm picking an x value and measuring the height there. So that's the height of my rectangle. So this whole thing is the area of a rectangle. And then we're just adding them all together. So this is just a really abstract way of presenting what we did before. This is the width of how wide the base is. This is the height, which we got by picking a point and evaluating the height of the curve. And then we add them all together. And now that's an estimate, right? The actual way we find the value of the area is we just run a limit on this. We say, do this estimate and then keep doing it with more and more rectangles. Do it with 100 rectangles, see what you get. Do it with 1,000 rectangles, see what you get. Do it with 1,000,000 rectangles, see what you get. Are they all headed towards a specific number? If so, that number is the area. So we're actually giving a definition to area that involves a limit process. Basically, we're saying approximate using rectangles, keep doing that over and over again, and run a limit on your answer. And it's possible to do this just through really clever calculations. So I'm going to show you how to do this. And this is just a demonstration, right? So I want to show you that it's theoretically possible to run this using a lot of algebraic cleverness and limit techniques, but we are going to learn better ways. So I'm going to do this same example with a right endpoint, but I'm just going to say they're n intervals. So I have f of x is 225 minus x squared on the interval from 0 to 12. And I'm going to use n intervals. So that means my width of each one is 12 over n. And let me add some pages, right? This is a demonstration for you to watch. Do not worry about copying along this, right? I am warning you, you are not going to have to do this, so don't waste your time copying. I want you to be aware that it is possible, but I don't want you to worry about doing it yourself. So I'm going to copy this onto another page. Right? I want to do this as a demonstration so that you realize it can be done, but we're going to learn a much cleverer way of doing this, more clever. So sort of our schematic here was here's our base from 0 to 12. Here's our curve up top. I'm dividing this into n intervals. So each one has a width of 12 over n. So my first one would end at 12 over n. And then my next one would end at 24 over n. And then my next one would be at 36 over n. And I don't know how many there are, I'm being abstract. My last one would end at 12n over n. So you might notice that all of my right endpoints have the form 12k over n. Here's my first one, here's my second one, here's my third one. I'm just counting by 12 over n. 12 over n plus 12 over n plus 12 over n. Eventually that gets me to 12 if I do it n times. So let's think a little bit abstractly. Here is my kth rectangle. And here is its base. This point right here would be 12k over n. I have added 12 over n k times. So here would be the top of my rectangle. So for my kth rectangle, the base, like all of these, is 12 over n units wide. And my height would be f of 12k over n, which is 225 minus 12k over n squared. So my area for the kth rectangle would be 225 minus 12k over n squared times 12 over n. So my total area estimate would be the sum as k goes from 1 to n. I'm now adding up all of those rectangles of each individual area computation. So now I'm going to do a lot of algebra here. So this is the sum as k goes from 1 to n of 225 minus 144 k squared over n squared times 12 over n. This is the sum as k goes from 1 to n of 225 times 12 over n minus, I'm just distributing this 12 over n, 144 times 12 times k squared over n cubed. I'm not going to bother evaluating 225 times 12 or 144 times 12 right now. At the very end, when I feel like I'm building towards an answer, I'll pull out a calculator and do those. Okay, let's split these up. So this is the sum as k goes from 1 to n of all of these guys added together. And then I can subtract the sum as k goes from 1 to n of all of these guys added together. Now, let's notice here, this doesn't have a k in it. So this is say count from 1 to n and every time add this. So when k is 1, I have this. When k is 2, I have this. When k is 3, I have this. I'm just adding this together n times. So this first thing here is n times 225 times 12 over n. If there's no k, we're just adding the same thing to itself over and over and over again. Now over here, I'm going to do a little trick where I'm going to notice that 144, 12, and n cubed don't have a k in them. I can pull those outside. That won't affect my answer. Over here, we'll notice the n's cancel. So I have the number 225 minus 12. At some point, I'll need to compute that. 225 times 12. At some point, I'll need to compute that, but right now I'm being lazy. Here I have 144 times 12 over n cubed. And let's just make sure we understand what this means. K counts from 1 to n, and I have k squared. So this is 1 squared plus 2 squared plus 3 squared, etc., all the way up through n squared. And with familiar patterns like that, there is a formula. And I don't care if you have that formula memorized. You know, this is something I sometimes remember and sometimes don't remember. Sometimes I have to look it up. But I will just tell you, if you are adding together from a really simple pattern, somewhere someone has figured out the formula. So the formula here, I will just tell you, is n times n plus 1 times 2n plus 1 all over 6. So that's just a formula you can check. Just trust me on that one. Actually, I'm double checking in my head because I have not looked this up. Yeah, that's fine. All right. So, and while we're here, I'll just notice that the 12 and the 6 provide a nice little bit of cancellation. So what we have here is 225 times 12 minus 288, because what's left is 2, 144 times 2, times n plus 1 times 2n plus 1 over n cubed. So what this is my estimate of the area with n rectangles. Right? What I'm finding here is the total area estimate. It's the sum of all those rectangles. But how do we find the actual area of the region R, the true area of the region R? It's the limit of this. Here, I intentionally didn't say how many rectangles I'm using. If I'm using 10, it's a pretty good estimate. If I'm using 100, it's a very good estimate. If I'm using 1,000,000, it's a ridiculously good estimate. What's the true answer? It's the limit of this process. So we're going to take the limit as n goes to infinity of this computation. Now, let's think about this. This is just a constant, so in the limit, it's whatever constant it is. Over here, we'll notice if I multiplied this part out, it would be, so we're treating n as our variable, it would be a polynomial that begins with 2n cubed. And down here we have n cubed. So top and bottom have the same degree. Hopefully you remember the rule is we just cancel it off and look at the coefficients. So the top basically has 288 times 2n cubed. The bottom has n cubed. In the long run, all those other terms don't matter. And so the limit is just the coefficient for the top over the coefficient in the bottom. And that's 288 times 2. Okay, so now we'll finally evaluate this. So this, if I'm not mistaken, let's see, so this is 2,700, if I'm not messing that up. And then this would be 576. So when I subtract, that would be 2124. So that is the true area of R. It is not an estimate. We took an estimate and we ran a limit on that. So there is a ton going on here. We have to abstractly think about what's going on. We have to write out the formula. We do a bunch of algebra. At some point, we probably have to look up some formula. We have to remember some limit rules about end behavior and polynomials and rational functions and all of that stuff. But I got an answer. 2124 is the true answer. And it turns out that this estimate, this middle estimate, was really good, right? We're in the thousands and we were off by only 4. So that turns out to have been really close to the true answer. But the true answer can be found. So here's what I want you to file away in terms of what's valued in this class. I want you to understand, generally speaking, how this works. On the AP, you'll probably be asked to do this, probably with no more than 5 intervals. They want to make sure that in theory, you understand how this practice works, how this process works. I also want you to know that in theory, we can roll up our sleeves and do a lot of stuff to compute this, but that's not how you'll be doing it. You're going to learn a really important theorem. Right? The theorem is called the fundamental theorem of calculus. Right? That is not a modest name. So coming up soon, you will see the fundamental theorem of calculus, which will basically provide a shortcut for how can we get an answer to a process like we just did in a much more straightforward way that's somehow tied into derivatives. Right? This process I went through used the idea of a limit, but it didn't really talk about derivatives or antiderivatives, so it doesn't feel all that calculus-y. The fundamental theorem of calculus is going to say, all right, this process where we're adding together all these rectangles, there's a different way to do it. And if you understand derivatives and antiderivatives, you're going to save yourself a lot of time. So just as some quick practice, here's what I want you to do. Think about the region bounded by the x-axis and below y equals x squared between x equals 1 and x equals 7. So I'll draw a quick schematic. You should be able to draw your own pictures. Sometimes they will be provided, sometimes they will not be provided. So here's y equals x squared. This is just the schematic. Here's 1, here's 7. These are vertical lines. So it's basically this region. And two things. So first, I want you to estimate the area using 3 subintervals and a midpoint approximation. And then I want you to do it with 6 intervals and a left endpoint approximation. So pause and try these. And if you want to skip the last arithmetic step and just present your answer, that's fine. That's actually good practice for what you would do on the AP. They might ask you a problem like number 1, and they don't really care how simplified your answer is. They want to see the process. So I hope you have paused to try this. Before I end this video, I will go through this. So for number 1, we'll just notice that if there are 3 intervals, this is 6 wide, each one has a width of 2. And if we're using midpoints, so if we were using midpoints, my midpoints would be at 2 and 4 and 6. Here's my first interval, goes from 1 to 3, 2 is its midpoint. My second interval goes from 3 to 5, midpoint at 4. My last one goes from 5 to 7, midpoint at 6. So we could just say that our estimate here, all right, E sub 3 is an abbreviation for estimate using 3 things. That's kind of informal. It would be f of 2 times 2 plus f of 4 times 2 plus f of 6 times 2. Height at the midpoint times width plus height at the midpoint plus times width plus height at the midpoint times width. So that's 4 times 2 plus 16 times 2 plus 36 times 2. Just leave it like that. No one really cares about your arithmetic. They just want to see the process. If you leave your answer like this, it's very obvious what you did. For number 2, we've divided it into 6 intervals, so each one has a width of 1. And we would be using the left endpoint approximation. So our left endpoints are at 1, 2, 3, 4, 5, and 6. 7 is a right endpoint, so it doesn't count. And each base is 1 unit wide. So that works out to 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared. This would be fine. Right. Any answer that just uses arithmetic, so don't leave function notation in your answer, don't leave trig notation in there, certainly don't leave any calculus notation, but if you're just presenting something that's clearly arithmetic, you can leave it like that. Later on, we will talk about how to actually find that area. Right? These are 2 estimates. If you compute them, you'll notice they're in the same ballpark, but not literally the same number, most likely. Maybe they are, I haven't checked. But we will learn the true area later on. Okay, that is the end of this video.